Okay, so number 18, it asks us to approximate the definite integral from 1 to 3 using the midpoint Riemann sum, and it gives us three subintervals, 1 to 1.6, 1.6 to 2, and 2 to 3. So those are going to give us our delta x. The first delta x is 1.6 times minus 1, which gives us 0.6. F of 1.3, the 1.3 being the midpoint of 1.6 and 1, means cosine of root 1.3. And then we do 2 minus 0.6, which is 0.4. That should be scribbled there, but it's not. That's a 0.4. And cosine of the value at that midpoint, so cosine of root 0.18 or 1.8. Plus, we do 3 minus 2, so 1 times cosine of root 2.5. So the midpoint is just the middle of these two values, and then we evaluate using our calculator, and we get 0.331. Okay. The next one is trapezoidal. It's a little more difficult, but not too difficult. And I want to draw a quick diagram up here of what a trapezoid estimation is going to be. So if we have a curve like this, and we're estimating using 3 trapezoidals, we are still looking for our delta x. We're still going to do our delta x. We have our first function evaluated here. I'm going to say f of base 1. And then our second function evaluated here, that's f of base 2, so on and so forth. So really, it's important to understand what's going on with the trapezoidal estimation and not really memorize the rule. We have the same subintervals, right? So our delta x is going to be the same. That's right here. The first delta x is the same as before, which is 1.6 minus 1. And our first trapezoid is f of 1, that's our left-hand function, plus f of 1.6, all divided by 2. So really we're looking for the average of these two heights that we multiply by our delta x. So this is our average of these two heights, all right? And then we add it to the next one. Again, our delta x is right here, 2 minus 1.6. And our next two values are 1.6 and 2. So it's these two values right here. So remember, our intervals were 1, 1.6, 2, and 3. Okay? So we have, again, do our delta x, which is 2 minus 1.6. That's going to give us this delta x here. And we find the average of these two, which is going to be the average of this height plus the average of this height divided by 2. That is our second trapezoidal estimation. And lastly, our third trapezoidal estimation is 3 minus 2. That's this delta x right there, times f of 2 minus, or plus f of 3, the average of these two, all divided by 2. And then it's a matter of plugging it into our calculator. Now, we don't have the exact same values as before because we're going to use root 1. We're going to use the endpoints root 1.6, so on and so forth. And this should come out to 0.342. This is going to be very similar to our midpoint approximation. So don't be thrown off by the fact that it's about the same. Okay. Okay, the next thing is it gives us our first derivative. It is known for f prime equals sine of root x over, negative sine of root x over 2 root x. And then the second derivative is sine of root x over 4x root x minus cosine of root x over 4x. All of this goes immediately into our calculators, okay? And then it says, would a trapezoidal approximation from 1 to 3 be an overestimate or an underestimate of the value? Give a reason. So the first thing we have to identify is the concavity of that interval. And what we find out is the second derivative is concave up or is positive from 1 to 3. And if it's concave up, then we know it's an overestimate. We know it's an overestimate. The trapezoidal estimation is an overestimate. Now the reason that is because the increasing or decreasing behavior does not impact whether a trapezoidal sum is an overestimate or underestimate. So for example, if I have concave up here, then the trapezoidal estimation will be an overestimate because we're going to be a little bit bigger than that graph. If it's concave up but decreasing, again, a trapezoidal estimation will be an over estimate. So the fact that it's increasing or decreasing does not matter in that interval. Okay, part D says, write the integral 1 to 3 of f of x dx as the limit of a right-hand Riemann sum with n subintervals of equal length. So what we did on the previous problem in unit on part A is we went from the right-hand Riemann sum with n subintervals, and we used limits to write the integral. Now we're going from the integral to the Riemann sum. Okay? So the first thing we need to do here is we need to determine delta x. So, which is equivalent event when we use a limit, delta x becomes dx, which is an infinitely small change in x. Okay? So our delta x is equal to our interval 3 minus 1, or 3, 1, so we do 3 minus 1, divided by n, or 2 over n. So that is our delta x, okay? Then we want to, this is going to be common throughout. The limit is obviously going to be the limit as n approaches infinity. This part right here, k equals 1 of the summation to n, is going to be the same throughout. Function f of 1 is our starting value. So k equals 1 is our right-hand estimate. 1 will be our starting value because we're starting at the value of 1. So this one, k equals 1, is because we're doing a right-hand Riemann sum. If it were a left-hand Riemann sum, it would be k equals 0. This one refers to the starting of the integral, okay? Plus k, which is the step we are on, times the delta x. So if our delta x is 3, then we multiply k times 3. We keep moving over every 3 to evaluate our function, and we multiply this whole thing by delta x. So this general part we don't necessarily have to write down, but that's where we're going. And then we rewrite the same thing. The limit as n approaches infinity stays the same. This part stays the same, k equals 1 integral of n. But instead of having the general notation for a function, we now have the actual function, which is cosine of the square root. This is our starting value. All right. So remember, we're talking about breaking this up into an infinite amount of rectangles. And we start on the left-hand side, which is 1, and then we move over k times delta x. Well, our delta x is 2 over n. K times delta x is 2k over n. All right, or k2 over n. Either one is fine, right? But that is our first estimate, and if we're talking right-hand estimate, we're starting at 1, we're moving over that much. And then this whole thing is times our delta x, 2 over n. So again, the k is our number of steps, times our delta x, and our delta x out here. So these two things, the 2 over n and the 2 over n, will be the same. And that's our answer. Let me go over it one more time. We take the difference of here to find our delta x. That's our 2. We divide that by n. That's our n subintervals. So whatever n subintervals is going to be our delta x. We then take this information and we apply the limit to it. So we say, wait a minute. If we have an infinite amount of n's, or if our n approaches infinity, we have an infinite amount of subintervals, then we're essentially doing the limit as n approaches infinity of the summation of adding up these functions, these rectangles, and the function generally is 1 plus k delta x times delta x. We know our delta x to be 2 over 1, therefore this becomes 1 plus 2k over n, and we know our function is cosine of root x, therefore this becomes cosine root of that whole thing times 2 over n. All right.